Imagine leaving our world behind. We float past the Moon, Mars, and Jupiter, our solar system shrinking to a distant speck. We travel through the Milky Way, a city of 100 billion stars, toward a place where physics is pushed to its limit. Our destination, the death of a massive star, a cataclysmic explosion that will give birth to a black hole. For eons, black holes have been cosmic mysteries, points of infinite density, gravitational prisons from which nothing escapes. We've seen their effects, but never their birth. The event is too fast, too violent, hidden deep within a dying star. But what if we could watch, second by second, as a star's core collapses and a singularity forms? Here on Earth, scientists have built a universe inside a machine, a supercomputer simulating this moment of cosmic creation. For the first time, we can witness the complete story of a star's death and a black hole's birth. This is not just about stars and gravity, it's about human curiosity and our quest to understand the cosmos. Prepare yourself. We're about to travel back in time and across unimaginable distances. We'll stand at the edge of an event horizon and watch as matter is crushed out of existence. The star's core is unstable. The countdown has begun. The secrets of a black hole's birth are about to be revealed, not through a telescope but through the calculations of a machine. The show is about to begin, and it promises to be the most spectacular event in the cosmos. Black holes have haunted our imagination for centuries, the ultimate cosmic abyss, a one-way door in the universe. Einstein's theory of general relativity showed us that massive objects bend space-time, but a black hole punches a hole right through it. Once you cross the event horizon, there's no return. The challenge: how do you observe something that swallows all light? Astronomers look for clues: stars orbiting empty space, matter glowing in X-rays as it spirals toward doom. But these are after-the-fact observations. The birth of a black hole is hidden inside a collapsing star, a supernova. The explosion acts like a curtain, hiding the drama at the core. The crucial moments are over in seconds, shrouded from view. For decades, the birth of a black hole was a black box within a black box. Our theories gave us an outline: a massive star runs out of fuel, its core collapses, and a black hole should form, but the details were a mystery. How does the core implode? What shockwaves are produced? How is energy distributed? Without seeing inside, our understanding was incomplete. We needed a new kind of eye, one that could see through the fire and fury of a supernova. Enter the era of simulation. With powerful computers, we can now peer into the heart of creation. The black box is about to be opened, and the universe's greatest vanishing act will finally be revealed. When telescopes aren't enough, we build new eyes, machines that see with mathematics. Meet Fugaku, a supercomputer in Japan, capable of hundreds of quadrillions of calculations per second. Fugaku can model the complex physics inside a dying star: gravity, nuclear reactions, fluid dynamics, magnetism, and more. Scientists use it to build a virtual star, 30 times the mass of our sun, and watch its fate unfold. The simulation tracks every particle, every flow of energy, every warp in space-time. It's not just a pretty picture, it's hard data. Media Group. Data visualizations of temperature and pressure maps from simulations. Scientists examining detailed simulation outputs at its stock, distribute equally, temperature, pressure, density, gravity, all mapped in detail. Scientists can pause, rewind, and view the event from any angle. They can test theories by changing the star's properties and seeing what happens. For the first time, the black box at the center of a supernova is open. Fugaku gives us the key. The universe inside the machine is ready to give up its secrets. We're about to witness the impossible, the birth of a black hole step by step. The simulation is our window into the heart of a dying star, and it's about to change everything we know. Our story begins with a blue supergiant, 30 times the mass of our sun. For millions of years, it fuses elements in its core, releasing energy that balances gravity. But when it creates iron, fusion stops releasing energy. The furnace dies. Gravity takes over, and the star's core collapses in an instant. The iron core, Earth-sized but with the mass of our sun, falls inward at a quarter the speed of light. Temperatures soar to hundreds of billions of degrees. Atomic nuclei are crushed. Protons and electrons merge into neutrons. The core shrinks to a ball just a few dozen kilometers across, a proto-neutron star. This sudden compression creates a shockwave, rebounding outward. The shockwave begins to travel out, destined to trigger a supernova. But simulations show the shockwave often stalls, losing energy as it fights through dense material. The explosion would fizzle out, something else is needed to revive it. The star's fate hangs in the balance. The next moments will decide everything. The real drama is about to begin. The Fugaku simulation picks up at the critical moment. The shockwave is launched, but it's struggling. Behind it, chaos reigns. A boiling cauldron of plasma, swirling with violence. Within this turbulence, massive spiraling vortices form, amplifying the star's magnetic fields. The magnetic field lines are twisted and bundled, becoming immensely powerful. This dynamo effect creates a magnetic jet along the star's axis, a magnetic tornado drilling outward. The jet gives the stalled shockwave the extra push it needs. The explosion becomes lopsided, stronger along the poles. The star is blown apart asymmetrically. All this happens in a few hundred milliseconds. The combination of rebound and magnetic jets overpowers gravity. The shockwave is revived, blasting the star's guts into space. The supernova has truly begun. But at the core, the main event is still to come. The birth of a black hole is imminent. As the shockwave tears the star apart, the proto-neutron star at the center is still under siege. Matter rains down, piling up mass second by second. There's a limit to how much mass a neutron star can support, the Tolman-Oppenheimer-Volkoff limit. The simulation shows the proto-neutron star crossing this threshold. In a fraction of a millisecond, its structure fails. Gravity wins. The core collapses into a singularity. A black hole is born. An event horizon springs into existence, expanding at the speed of light. Anything inside is lost forever. The simulation shows space-time warping as the black hole forms and grows. The black hole swallows the last remnants of the core. The entire sequence, from collapse to black hole, takes just over a second and a half. A star that lived millions of years is gone. A black hole, destined to last trillions, takes its place. For the first time, we see the universe's most mysterious birth in detail. This simulation is more than a cosmic movie. It's a Rosetta Stone for the universe's most energetic events. It helps us interpret the signals we see: supernovas, gamma-ray bursts, gravitational waves. The simulation shows how magnetically driven jets, powered by the newborn black hole, drill out of the star. When these jets break through, they unleash torrents of high-energy particles. Gamma-ray bursts. If a jet points at Earth, we see a brief, brilliant flash. The simulation explains the energy and jet-like nature of these bursts. It also reveals how asymmetric explosions send out gravitational waves, ripples in space-time. The simulation predicts the exact shape and frequency of these waves. If our detectors pick up a matching signal, we'll know we've witnessed a black hole's birth. This is multi-messenger astronomy light, gamma rays, and gravitational waves, all from one event. By combining these signals, we build a complete picture of cosmic cataclysms. The simulation turns chaos into a solvable puzzle, and it tells us exactly what to look for. The true power of simulation is bridging theory and observation. For years we had equations and telescope data, but a gap remained. The simulation fills that gap, turning physics into observable signals. Now we can compare simulation output with real data. The lopsided, jet-driven explosions match what we see in supernovas. The energy and duration of simulated gamma-ray bursts align with observations. It's like finding a video of a cosmic crime. We can now infer what happened inside a star from the signals we detect. The simulation gives us tools to decode the universe's messages. And as our models and computers improve, our understanding will only deepen. This feedback loop between theory, simulation, and observation drives science forward. Where do we go from here? The future of astronomy is brighter than ever. New telescopes and detectors will probe these cataclysms with unprecedented sensitivity. We'll catch supernovas as they explode, detect gravitational waves from black hole births, and build a catalog of these events. We'll begin to understand the diversity of black hole formation. Do all massive stars form black holes this way? How do spin and mass change the outcome? The Fugaku simulation inspires even bigger questions. Can we simulate the first stars, the creation of heavy elements, the dance of galaxies? The possibilities are as vast as the universe itself. We are cosmic archaeologists, reading stories written in light, gravity, and space-time. The journey is far from over. What other secrets is the cosmos waiting to tell us?